Greetings from Chile. I'm Jorge Grempin, Assistant Professor at Pontificia Universidad Católica de Chile, Department of Structural and Geotechnical Engineering. I'm also a researcher at CIGIDEN, and my collaborators are listed below. I'm going to talk today on risk assessment platforms that we've been developing in Chile, namely DRW, ASISTE, and VRC, all acronyms, and they are the collaboration of several researchers that are from different backgrounds. These collaborations merge the subjects of seismology, engineering, economy, urbanism, and computer science. In the last decade, after the 2010 Maui earthquake, magnitude 8.8, what we have been doing recently is characterizing the different consequences on the level of physical, economic, and social context. These objectives have been accomplished using computing platforms. We've integrated different methodologies, data that we've recorded all along Chile in the subduction zone, scripts as well from different researchers developed at CIGIDEN and also externally developed. Our main purpose for all of the platforms is research purposes. Results that we have obtained aim to help decision makers eventually. The urbanistic, economical, and civil protection strategy. So we have developed based on several existing risk assessment methodologies. We have validated them scientifically within the realm of CIGIDEN and also with external researchers. We have focused solely on risk metrics, and with this, the development of a calculation engine which integrates all of these methodologies, data, and script codes. We focused solely on seismic and tsunami hazards. This is what we call DRW. We've also looked at different visualization platforms which are focused on specific users for urban planning at different scales, specifically local. The users are decision makers. For economic losses, we've been focusing on a national scale, and some of the platforms that we've been developing are ASISTE and VRC. And for that, we can break it down into three parts: hazard, exposure, and vulnerability, all of which integrate into risk. So hazard, we define as the probability that a certain intensity measure exceeds a threshold in a certain period of time. Exposure is something that we've been working on different levels with different databases, namely georeference and simplified models that contain the characterization of elements, systems, or persons exposed to hazards. The vulnerability, we look at how these systems, these elements, or persons which are exposed to the hazards can become damaged or injured, or the expected economical losses that we can suffer. And all of this we quantify and we can calculate the risk. The risk metrics are mainly within the realm of DRW, calculation engine that integrates multiple modules. Each of them run a different problem. And all of these can be summarized in the following items. We can characterize them as hazard, exposure, vulnerability, and finally our objective is risk. And each module is independent from each other and has its own inputs and outputs. In addition, some static data are required, especially the exposure module, which eventually changes, and we plan to keep track of these data of exposure by using automated systems. So from the perspective of the application of DRW, we focused on San Antonio, a city that is in central Chile. It's coastal. It has a very large port that is going to be expanded into a megaport. And through this port, many goods such as copper and agricultural produce exit Chile to the world. From the hazard perspective, our main goal is to generate a synthetic earthquake catalog that is physically consistent to the Chilean subduction zone. We use this catalog to generate earthquake seismic intensities as well as tsunami inundation intensities. To achieve this goal, we use two approaches that intersect. The first approach is to perform physics-based simulations of the earthquake seismic cycle on the Chilean subduction zone. With these simulations, we can achieve realistic earthquake sizes and timings within a span of time. The second approach is to use existing GPS and radar data which are used to measure the true deformation of the Earth's surface, from which we can determine a degree of coupling between the South American and the Nazca plate. We generate multiple rupture scenarios which respect the physics of the subduction zone, and each of these rupture scenarios are defined by magnitude and hypocentric coordinates, and we draw scenarios using a Monte Carlo simulation. So with the synthetic catalog for each hypocenter and magnitude, we simulate a rupture slip distribution. And from these several rupture scenarios, we calculate free surface displacements using different physical techniques. To calculate seismic intensities, we have been using a simulation technique that uses small earthquakes and sums them up according to the slip rupture process on the fault that generated the ground motion produced by a larger earthquake. This method is called the empirical Green's function technique. The top left figure shows in green the seismic stations that recorded ground motions for a small earthquake and for the main shock. The blue and red rectangles show regions within the seismic interface that radiated large quantities of seismic energy. The seismograms to the right depict ground motion velocities at different stations produced by small earthquake, and the figures below show observed ground motions produced by the 2015 magnitude 8.4 EFL earthquake, and in red the synthetic simulation obtained using the empirical Green's function technique. We can see great resemblance between observations and synthetic generated ground motions. This is possible due to the great instrumentation program run by the Centro Sismológico Nacional, CSN. Top figure, you can see stations that are distributed all over Chile, the distribution of magnitudes and the number of events in the plot below. And from there, you can also see on the middle figure the magnitudes of earthquakes that have been recorded. And to the right, the stations and how many ground motion observations have been recorded on each of those stations. This is a great wealth of data that has been used to develop different ground motion models. There are several now that have been developed in Chile, and we use these models as well to relate magnitude and distance from the source to a specific site with a ground motion intensity measure, namely peak ground acceleration or spectral accelerations at different periods. Also, with the same earthquake source models, we have been developing simulations using different numerical techniques to propagate tsunami waves produced by the earthquakes. Bottom movie shows more complex models of inundation in the same cities. You can see all sorts of phenomena are produced on the coast and inundation of the streets within the city. From this type of simulations, we can obtain to the left seismic intensity measures, namely peak ground accelerations. And you can see, for example, for the case of San Antonio, different intensity measures that vary from 0.2 to 0.8 Gs. From the point of view of inundation, we have maximum flood depth, which is shown in the same region. So the important thing about this is that both the seismic and tsunami intensity measures are consistent with the same sources. So going back to the San Antonio case and the DRW method, we have the next step, which is exposure. And we use georeference simplified models, which characterize the exposed inventory buildings mainly. We separate and classify them through material structural system, building heights, design levels, quality, which reflect on the quality of construction, the year of construction. We're inspired by the HASIS FEMA 1999 method. We use very similar ways to classify and the same type of building taxonomy to characterize a building typology. We've been using several databases within Chile to characterize the building typology and design level distribution. For example, in San Antonio, we've been working on pilot programs on other Chilean cities such as Viña del Mar. And from the vulnerability point, we are constructing fragility functions for all of our building typologies. We use mainly capacity spectrum method, but we've been looking into other methods as well to compute different probability damage states. These are some of the scenarios that we've been computing. We can see here from many scenarios, we calculate the probability of reaching a damage state level in percentage. So we see to the left slight and moderate damage all combined, and to the right we see extensive and complete damage as probability of being reached within a specific amount of time, in this case in 50 years. We can see that there's great probabilities of reaching extensive and complete damage within 50 years. And from these, we've implemented different techniques for state valuation, and from these, the exposure and true cost of buildings in this region, we have been able to calculate direct economic losses. Human evacuation models are generated as outputs for assessing different evacuation routes and the evacuation times to safe zones to prevent fatalities. We've done this in conjunction with census population and other information that can tell us during day or nighttime where populations are mainly located. Given different velocities of each of the agents, the least cost distance model, we've also looked at network models with pedestrian congestion. All of this is steered by more complex agent-based modeling and taking into consideration real physics-based inundation of the different roads and within the city. With respect to risk, we use the physical damage, the amount of injured people, and we can estimate from these economic losses. As you can see here, we show the final economic loss in percentage of the total appraised values. This information is extremely difficult to assess for people that are not experienced, so this is why we've been working with different partners in the visualization of these results through online platforms. We have mainly devoted our efforts into urban planning at the local scales and for the purpose of economic losses at national scale. So what is ASISTE? It's a pilot platform for seismic tsunami evacuation, and we focus mainly on purposes of urban planning. We obtain standardized seismic tsunami evacuation risk metrics. We aim to help improvement of regulations specifically for risk study requirements of urban planning. The beta test version of ASISTE, where you can visualize all sorts of information regarding the risk. Physics-based hazard, consistent from the point of view of tsunami inundation and ground motion intensities, using a unique earthquake rupture source. It considers the true exposure across Chile and the vulnerability for different structural typologies. All of these efforts are computing engines designed for research purposes for now. The visualization platforms are designed for decision makers. The risk assessment methodology includes risk metrics, calculation engine, DRW, and the visualization platform. Any questions or comments that you may have regarding the ASISTE, VRC, and DRW platforms are more than welcome. Any suggestions for improvements and also ideas for future collaborations are extremely welcome. Thank you.